This is another moment about a point in 3D problem. So here we have another wireframe box given with its dimensions, and we have a force that is acting from point B to point A, and it has a magnitude of 17 kilonewton. And we're again given the dimension of the box. So we have to start out by finding the Cartesian vector representation of the force F. So let's see. To do that, what do we have to do? So this one is a truly three-dimensional vector, so I'm pretty sure we don't want to try and do that geometrically. So we'll just get the unit vector from B to A. So we have to start out with a vector, the position vector RB. RAB is equal to RA minus RB. So that is RA. Let's see. Where do we go? We have to go in the x direction from the origin to A. Right? We're 2 meters in the I direction. 2I. Don't have to go anywhere in the y direction. 0j, and we're also not going anywhere in the z direction. 0k meters minus, want to go to B. We don't go anywhere in the x direction, so 0I. We go in the y direction, so plus 4j. And then we also go 1 meter in the z direction, so plus 1k meters. What does that give us? 2 minus 0 is 2, so 2i. 0 minus 4 is minus 4. And then 0 minus 1 is minus 1. No, it's not. We're not asked for the position vector, so this is not really a final result. So that means we now, to get the unit vector, we need to know the length. So RAB is equal to 2 meters squared plus minus 4 meters squared plus minus 1 meter squared, and that is square root of 21 meters. So once again, we don't get a nice integer here, but we can use that nonetheless. We'll just leave it as a fraction, so we can say our UAB is then 2i minus 4j minus 1k meters divided by the square root of 21 meters. So we get 2 over the square root of 21i minus 4 over the square root of 21j minus 1 over the square root of 21k. So that would be our unit vector. And now if you want to get our force vector, right, then we can say F is equal to our unit vector times the magnitude. So F times UAB. And so that would be, what was the force? 17 Newton. 17 Newton times 2 over the square root of 21i minus 4 over square root of 21j minus 1 over the square root of 21k. So that is then, let's see, that would be 34 over the square root of 21i minus 68 over the square root of 21j minus 17 over square root of 21k, and all this is Newton. And if you write that as decimals, then we get 7.419i minus 14.839j minus 3.710k Newton, and that would be our Cartesian vector f. So that was the first thing that we were asked for. All right, so we know that we're going to do B. Let's see what B asks us to do. B says give a position vector pointing from the origin to the line of action of F. So the line of action of F, right, goes through A and through B. So we can choose either one. I would suggest we choose A because there's only one, the X component. Right? If I want to go from the origin to B, I have to go both in the Y and the Z. For A, I only have to go in the X. So I would suggest we choose our A. So that is then equal to, let's see, 2 meters in the X. So 2I plus 0j plus 0k meters. So that would be then C. Let's see, what do we do here? Give a position vector from point C to the origin. All right, so let's see. We can either go from C to A, or we can go from C to B. I would say we go to A because, again, we'll just, is the easier one to do. All right, so we can say we want, what do we say? We go from C to A, so our AC is equal to, don't need a bracket there, RA minus RC. RA, we'll just have it written there, so we'll just copy that over. 2I plus 0j plus 0k meters minus, how do we get to C? Well, we have to go in the 2 in the X direction and 4 in the Y direction. So it'll be 2I plus 4j plus 0k meters. So that is then 2 minus 2 is 0. 0 minus 4 is minus 4. And 0 minus 0 is 0. And meters. Now, does that make sense? Well, if we want to go from C to A, all we have to do, it goes backwards 4 meters along the Y direction, and we're there. So that's exactly what this says. So that's all good. Then let's do D. D is determine the moment vector MO of the force F around point O. All right, so we have everything we need there, right? Because we know that M of the origin is going to be any position vector on the line of force. We said we're going to choose RA, and that's crossed with F. All right. So then we can write that as our matrix again. Well, we know we have I, J, and K. Then RA is our next one, so it'd be 2, 0, 0. Now we can see why we like to use something that's simple. A lot of zeros drop out. And then here we have 34 over the square root of 21. We have minus 68 over the square root of 21 and minus 17 over the square root of 21. And then our little crutch here, so I and j, 2 and 0, 34 over square root of 21 minus 68 over the square root of 21. All right, so let's see what we get. Let's see. Our first one is this one. That's 0, so that's good. I times 0 times minus 17 over 21. Then this one is 0, 2. That's nice, but we'll write it down anyway just for completeness. Times 0 times 34 over 21. This one is not 0, so it'll be plus k times 2 times minus 68 over square root of 21. And then the upstrokes, another 0, so it'll be minus 34 over square root of 21 times 0 times k. And another 0, that'd be minus, let's be careful we don't miss one of the negative signs. Doesn't matter because it's 0, but nonetheless, good to be correct. 61 over square root of 1 times 0 times I minus the last one, which is not 0, minus 17 over square root of 21 times 2 times j. All right, let's see what we get then. We get that I is 0, that j is 0. We have a k. Do we have an I? We don't have an I. All the i's are 0, so I'll write that in. That j is 0. This one is not 0. It is negative. Negative is plus. 17 times 2 is 34. So it'll be plus 34 over square root of 21 j. And then what is our last one? K, let's see. K, there's, that one has a value. This one doesn't. This is a 0, so 62 times 2 would be 120, 136 minus 136 over square root of 21. K, oops, we forgot all of our units here. So this was all in kilonewton times meters. Kilonewton times meters. Kilonewton meters. And so if we do decimals, then we have 0i plus, why do I have a plus there? Oh, there we go. I have a typo in my notes. Plus 7.419 j, and then minus 29.68 k kilonewton times a meter. And that's the moment about point, the origin point, M, right there. All right, let's see what else that we have to do. We have to do the same around C. Well, we already created a vector. That was our vector RAC. Again, it's a relatively simple one. So let's see what we get there. Let's see, so that would be part E. So then MC is RAC crossed with F. Right, that's what we got. Again, instead of doing AC, we could have done BC as well, but would have gotten us more components. The result would be exactly the same, but just means we'll have to do a little more calculations. All right, so what do we have? We have I, J, K, RAC, we can no longer see, so that was 0 minus 4, 0. 0 minus 4 and 0. If we scroll up just a little bit, we have our F there. 34 over square root of 21 minus 68 square root of 21 minus 17 square root of 21. And then our extra pieces here, I, J, 0 minus 4, 34 over square root of 21 minus 68 over the square root of 21. All of this kilonewton meters. All right. And a lot of writing. I think this time we'll just drop the zeros so we don't have to write quite so much. So that's our first one. So that would be I times minus 4 times minus 17 over square root of 21. This J is 0. This K is 0. So let's do the upswings. That is not 0. So it'll be minus 34 over the square root of 21 times minus 4 times K. This one is 0 and this one is 0. Well, that makes it nice and easy. So no component in the y direction this time. Oh, and let's not forget units. Kilonewton times meters. If we multiply all this stuff out, then let's see what we get. We will get minus and minus is plus. 4 times 10 is 40, so 67 times 4 is 28, so 68 over square root of 21 times I, and we said we don't have a j, so 0j, and then minus plus minus is plus. That would be times 2 is 68 times 2 is 136 over square root of 21 K kilonewton times meters. Again, we can express that in decimals. 14.839 I plus 0j plus 29.68 K kilonewton meters. So that's our moment around C. Let's see what else we have to do. So that was the moment. So F is give the shortest distance around the point O and then around C. All right. So that'd be E, F. Now, if we want to do shortest distance from the line of action to point to the origin, then we first have to find the magnitude of the moment. So MO equal to wherever we had that. Does it fit? Does it fit just about? So this time we'll I'll write this out, so it'll be 0 kilonewton meter squared. No, it just does not fit if we want to use the actual values. Plus 34 over 21. Kilonewton meter squared plus minus 136. Minus 136 over square root of 21. And that gives me 30.591 meters. That would be kilonewton meters. I'm sorry, we're not done yet. That's the magnitude. So if I want to have D0, then I can just do M0 over F. 30.591 kilonewton meters divided by, well, 17, right? Yep. Over 17 newton. Kilonewton, I'm sorry. Gives us a distance of 1.7995 meters. It's the shortest distance. And then G was the same thing for C, so MC is the square root, this one we should get on here, yep, of 68 over square root of 21 kilonewton meter squared plus 0 kilonewton meter squared plus 136 over square root of 21 kilonewton meter squared. And that gives me something very close, 33.181 kilonewton meter. So that means my DC is going to be MC over F, which is 33.181 kilonewton meters divided by 17 kilonewton, and that gives me 1.9518 meters. All right, with that we are done. So if we come back up here, right, we had this setup, and we looked at the force that is going from B to A, and we found what the moment is around the origin as well as around point C, and what the shortest distance would be between the line of action from B to A to the origin and to C.